A disk of mass m is given a velocity v, and the Planck is not having any velocity. So I'm giving a velocity v naught to the disk. Mass is m, radius is r. Since it is clearly slipping, as we can see, the downmost point of the disk is having velocity v naught because there is no rotation, only translation. And whereas our Planck is not having any velocity, so this is a slipping case. Since it is slipping, we have a kinetic friction, that is mu mg. Now it not only acts on the disk, it will also act on this Planck in right side. So this is mu mg. Since Planck mass is m by 2, as it is given, the mass of the Planck is m by 2. So I will write acceleration of Planck is mu mg divided by m by 2, which is 2 mu g. So this is the value of acceleration of Planck, and it is towards right side. So acceleration of Planck is towards right. Now let's try to analyze the disk. Now I'm taking the disk separately. I'm only writing the friction force. Let's try to apply torque about center of mass. You cannot apply torque about this down point because that is not your instantaneous axis of rotation and it has a tangential acceleration. It is not an inertial point. So we cannot apply torque about the downmost point. So we should only apply torque about center of mass. Now if you want to apply torque about the downmost point, we need to take pseudo force, pseudo torque and all those things. Instead of that, better to apply about center of mass. This is going to create a clockwise alpha as well as center of mass towards left as the force is towards left. For translation motion, I will write mu mg equal to MACM. So ACM is mu g. For rotation motion, torque about center of mass can be written as mu mg into r. This is equal to mr square by 2 into alpha. So from that, alpha into r alpha is 2 mu g. So we got the value of acceleration of center of mass and r alpha both. So now if you look at this downmost point, which is in contact with the Planck, it has two acceleration, that is ACM plus r alpha. Both are towards left only. And this value is equal to 3 mu g. But the downmost point velocity is right side, it is v naught. Initial velocity is right side v naught, and it is having an acceleration 3 mu g towards left. So velocity of this point, let's say this is p. So velocity of point p at any instant of time can be written as u plus acceleration of point into t. V equal to u plus at. So velocity of that point p, this is v naught minus 3 mu gt. So this is a point of contact velocity as a function of time. Now our surface or the Planck is having a zero velocity. Since this is a surface, I call this as velocity of surface, this point which is in contact with the disk. Since this is having an acceleration of 2 mu g right side, acceleration of Planck is 2 mu g right side. So I write velocity of surface is, since it is having zero velocity initially, 0 plus 2 mu g into t. Now for pure rolling, velocity of point of contact and velocity of surface both should be same. So from that I will write v naught minus 3 mu gt, which is equal to 2 mu g into t. So t is v naught divided by 5 mu g. So this is the time after which you are going to see pure rolling.